I welcome you all to the next session on quantum chemistry. In this session, we are going to talk about a very important phenomena which we see around. Anything which is having its own rotation or a motion around it, it is going to have a angular momentum, and that angular momentum can be calculated using the quantum mechanical operators, and it has lots of application you are going to see in the next few slides. I am going to talk about the angular momentum, its importance and why we have to study it. Then the very important concept of commutation in angular momentum, and then we will try to look at the quantization which we can see in angular momentum as well as the angular momentum in z axis or z component. So, in quantum mechanics we come across number of motion that is circular in nature and which is spherical. So, for example, we have a molecule which is rotating on its own axis, we can have a molecule which is rotating on its axis. It can be based on its bond or it can be rotating through a 180 degree around its. We can have a electron which is rotating or orbiting around a nuclei. We have a spinning electron that you are aware of, we can have a spinning nuclei as well. So, we come across in chemistry number of problems that has to deal with angular momentum. So, it is important for us to study it. So, what we are going to do in this session is that we are going to look at a angular momentum for a very simple system like a mass which is revolving with at a certain distance r. Let us look at the angular momentum operators. The angular momentum operator, if there are three directions x, y and z, we can look at the angular momentum operator Lx, which can be represented by minus I h by 2 pi, y curl by curl z minus z curl by curl y. Basically, you have to remember that if it is Lx, this two derivative is going to be other than x. That is the very important observation you can have on these equations. If it is y, you can easily see that the derivative terms are x and z. So, we have the three operator angular momentum operator which can be possible in 3 x, y and z direction. We have to look at what will happen when they commute or if they do not commute. Why commutation is important to know? Because we know that if the two operator commute, then they are going to have the commutation value is going to be 0, and if it is 0, they can be measured simultaneously. If I am going to have a operator which do not commute, then we cannot measure them simultaneously, and that is a difference between a classical mechanics and a quantum mechanics. There is L square which is the summation of all the square terms of x, y and z angular momentum, and it has been mentioned that all this will depend upon they commute or not is important because they can tell you that they can be measured simultaneously or not. Let us look at what are the terms we can measure simultaneously. Like if I have L square Lx, L square Ly and L square Lz, if we try to do a commutation of each term, we are going to get it 0, and which means that the total angular momentum and any of the component they commute and they can be measured simultaneously, but the individual component they do not commute. We are going to see this, we can prove this by a simple algebraic expressions. It is written here that these three terms do not commute, they are not equal to 0. So, they cannot be measured simultaneously. Let us try to look for a proof for what we have said just now. If we have Lx and Ly, these are the two operator in x and y direction. So, commutation means the order of the operation should not matter. So, Lx and Ly minus Ly Lx should be equal to 0, then we say they commute. So, we have shown an example where we can see they commute or not. So, it is L x L y the first term here. So, minus I h cross is h by 2 pi y curl by curl z minus z curl by curl y, then again minus I h cross z curl by curl x minus x curl by curl z. Basically, this is just a representation of each operator in x and y direction, and it is simple multiplication of first term with the first term here and the first term with the second term here, and we get a simple expression. And I h cross, when they multiply together, I am going to have minus I square h cross square, and we know that I square is minus 1. So, finally, when we expand the whole thing, we are going to get a expression which look like this, and it is just a multiplication of the derivative terms, and there are all the terms which is visible here. Then the second term, if you try to look at the L y L x, the order of the operator has been changed. So, it is going to have a very similar expression like minus h cross square z curl by curl x minus x curl by curl z, y curl by curl z minus z curl by curl y. The same way they will be multiplied, and we are going to get a expression which look like this. If we subtract the two terms, the resultant will determine they can be measured simultaneously or not, depending upon the value we get. So, when the two terms which you seen in the earlier slide and this are subtracted together, I have left with only one term, and this term can be separated out as I h cross and multiply by I h cross. Basically, it is the same minus h cross square, and I am aware that this whole term is equal to L z, that is the angular momentum in the z direction. And so, basically the commutation is going to give me a term, it is not turning out to be equal to 0, which means that L x and L y cannot be measured simultaneously. They have some value after the commutation is carried out on them. The other term that we are interested in is the total angular momentum. Does it commute with the angular momentum in the z direction? Then it is a simple expression, because L square is the square of each component term, and then it is L z. It has to be looked at a b minus b a type of expression. So, this whole term is going to multiply here, and this term is going to multiply with the whole term. So, we are going to get a sixth term which is visible here, and we can segregate the terms depending upon, like the two terms which are very similar can be segregated together, like L x square L z minus L z L x square. These two terms are taken together from the sixth term, and we have such type of three terms with us, and which means that this term can be written in the commutation form like L x square comma L z. Similarly, all other two terms can be written in this form, which what we are trying to do is that does L square commute with L z? If it commute, we are going to get 0, if it do not commute, we are going to get some values. We are trying to look at the L square L z term, they commute or not. So, earlier we have seen that the first two terms are taken together and they are giving us some value, then we have to look at the other way around. So, other way around means that you are going to have L square L z and the whole term has to be expanded like this. So, depending upon the expansion, I am going to have a term that is L x L z, then L x L z, there these two terms are there, and because they commute, I am going to have a term minus I h cross L y, and similarly I am going to have minus I h cross L y, and the terms can be taken together common minus I h cross. So, the two terms which remain inside can take you to another term that is minus I h cross L z, if we wish to do it further. Similarly, if we carry out the expression of L square y and L z, we are going to get an expression which is plus I h cross L x L y plus L y L x, and this term is, we know that this term is equal to 0. So, by adding all the three equation, this is a positive sign. If you remember the earlier slide, we have a negative sign, the expression remain the same, and this term, there were 3 terms. So, this term was 0. So, all the 3 terms when we add together, I am going to get a L square L z equal to 0, which basically suggests that the total angular momentum and the angular momentum in z direction can be measured simultaneously. That is a very important conclusion, and which can easily be derived if we carry out a commutation work with the angular momentum. The other thing that we are interested to know, that how to work with this angular momentum and find out their eigenvalue without going to the Schrodinger wave equation, and how are they quantized, that is an important question to be asked. These things can be answered if we try to work with a operator algebra. A simple operator is ladder operator. You will understand the meaning of ladder in the due course of time. Ladder means a simple L plus, it is a rising operator, and there is L minus, that is lowering operator. It is a operator which can be operated on another operator, and depending upon it is rising or lowering operator, it can change the value of the given operator. So, how they defined as L plus is L x plus minus I or plus I L y, and when it is L minus, it is L x minus I L y. So, plus sign is representing rising operator and the minus sign is representing lowering operator, and they can be operated on the angular momentum, and we will see that very important results can be obtained if we operate with the ladder operators. There are certain algebra that can be obtained if we carry out the interaction of L z with L plus minus. That is the way we can get a results, and L square L plus minus is 0, and if it is L plus minus and N minus plus, which basically means that it is rising and lowering, this is lowering and rising operator, they are commuted together, we get a value, and that is plus minus 2 L z. How this rising or lowering operator can change the value of the L z or L square, that is our aim to look at the total angular momentum or the momentum in the z direction. So, if we have a ladder operator algebra, it is L plus minus and L minus plus, they work together, it has been put here, they have a different sign, and we can just simply multiply the terms. We have L x square, L y square plus minus, depending upon the sign has been changed here, and we are going to have the two different L x L y and L y L x. So, this term we are aware that this term is related to L z. So, the first L x square, L y square plus L z square, these 3 terms are the summation, and if we want to replace it by L square, we can write this first 2 term as L square minus L z square. This is the expression we can get, and the last term is going to give us the H L z term. It is simple algebraic expression that we are working with. If we are interested to know what is the eigenvalue of the total angular momentum and the eigenvalue of the angular momentum in z direction, we can assume a simple eigenvalues, like for total angular momentum we have L square f, this is eigen function, and lambda h cross square and L z f mu h cross f. These two are just a representation of eigenvalue here, and f are basically representing the eigen function for both the operator, the total angular momentum operator and the operator in the z direction. And if we carry out the rising and lowering operator on the L square, you can see that L square is operated upon by rising and lowering operator. The L square can be taken inside. This L square f, you remember from the last slide, it is equal to lambda h square f. So, basically lambda h square can be taken together and we have a expression which is L plus minus f. So, I can simply say that the L square when operated upon by rising and lowering operator, I got a new eigen function and the eigen value remain the same. So, what happened when we have Lz? Lz can be operated upon rising and lowering operator. The same way this Lz can be taken inside and we are going to have a simple expression which can be solved easily, and I got a term which is having a value 1 more than the eigen value which we have earlier. What is suggests that just by applying the rising operator, we have a value which is more than the earlier value, or if we apply a lowering operator, it is going to have a value less than the earlier value. And that is the reason we call them a ladder operator, because they generate a series of values which is increased or decreased by plus 1 or minus 1. And we have seen that the Lz, the values are being changed, but the L square, the value almost remains same. So, as there will be a series of values for the eigen value of Lz, can we have a limitation? Can we have something which determine that the upper limit and the lower limit? That is important, because we cannot have an infinite series of values. So, how to find it out? We are trying to look at this L square minus Lz square, and these are the expression we already know that these two terms are equal to lambda minus mu square h cross square, the earlier expression, and we are going to have a square terms here, which suggests that we cannot have the value less than 0, their value is going to always be more than 0. That is a simple conclusion we can obtain from this, and depending upon this two value has to be more than 0. And when we put it here, we get a important observation that the lambda is going to be larger than mu square, and this is trying to put a upper and lower limit to the values that we can obtain. Let us try to look at the maximum value first. If I have a operator which is going to operate on the maximum value which I assume as f max, that is my eigen function having the maximum value, it should terminate, it should vanish if it is a maximum. If it is a maximum, we cannot have a value more than that, and same thing can happen here, but we know that L square term do not changes. When a rising or lowering operator is operated on that, the eigen value remain almost same. So, L square term f max equal to lambda h cross square f max, this L square term can be replaced by this earlier expression we have seen, and this is equal to each term can be represented by L square h square, this term can be represented by L h square f max. And we know that this term can be solved easily, we can take the term common, that is L plus 1 and that is h cross square. So, my lambda value has to be equal to L plus 1 h square. And similarly, what we do, if we do with a lowering operator, we keep on operating the lowering operator, the eigen value keep on decreasing, but we have to have a lower limit. Let us that lower limit we call it the function, we call it f mean, so that the moment f lowering operator is operated on that, it should become 0, otherwise there will be a value lower than that which is not acceptable. So, that is the reason we should be having a lowering operator and the f mean is the minimum possible value. So, this is the same way we are going to have the different values for f mean, and we can say that L square h cross square minus L h cross square f mean if we work with the minimum values, and which suggests that if we solve it, we have L minus 1 h cross square. So, we have a two sets of value, one for the rising operator which has a maximum value, and there is a one set of value that is the minimum value. Both the value when we compare, both are the eigenvalue of L square, and we are aware that the L square, the eigenvalue do not change, which means that the terms which we got L plus 1 or L minus 1, they need to be equal, and then when they will equal, when the L will be equal to minus L or L equal to L plus 1. These are the two possible conditions in which these two terms are going to be equal. So, we found two different types of set of values. One is minus L equal to L as well as L equal to L plus 1, but L plus 1 is not a acceptable value if you try to look at, because we say that L is the maximum value. We cannot have a value more than the maximum value. That is the reason we cannot accept the second solution. So, the first solution, that is L equal to n minus L, that is the acceptable solution for the Lz values, and we can easily see that it is values will lie between minus L to plus L, and the mu has going to have a 2 L plus 1 value, and that is the magnetic quantum number. We have not mentioned it what mu is, but it is magnetic quantum number, and its value is going to change from 2 L plus 1, and it is going to change by 1 unit from minus L to plus L. And if we try to look at, there will be integer just L equal to minus L plus n, where n can be half. So, we get a series of value. The earlier angular part of Schrodinger equation says that L can be integer, but along with integer we got another fractional values, which is a general expression for any angular momentum operator, and if even without knowing the eigenfunction. So, we have come across the different types of angular momentum and why we should study it, their importance in the chemistry, and we talked about what is the computation of angular momentum, why we should study it, their importance if we want to measure something simultaneously or not, and we found that L square and any other component can be measured simultaneously, but the individual component cannot be measured simultaneously. And finally, we have applied a concept of ladder operator to obtain the different eigenvalue of total angular momentum and the angular momentum along the z axis. So, this is a very important concept we have come across. In the next session, we will talk about the rigid rotator, their importance, and the system of rigid rotator, because they are the system which can be calculated or measured accurately using quantum mechanical operators.